Welcome back to Programming Fluency. This is section 8.4, Building a Linked List. Arrays are fast to read but slow to change in the middle. In this video, you will build a linked list from scratch, where inserting and deleting are just a few pointer changes. Let's begin. Welcome back. An array is fast to index but painful to change in the middle. To insert at position 3 in a 1,000-element array, you must shift almost 1,000 elements over just to make one gap. Deleting is just as slow. What if each element simply pointed to the next one? Then inserting or deleting would be a matter of changing a few pointers with no shifting at all. That is a linked list. In this video, you will build a complete singly linked list from scratch. You will define a node, link nodes together, traverse them, insert, delete, and free the whole list. Along the way, you will meet one of C's most important idioms, the double pointer. This is the plan for this video. First, the node, a struct that holds data and a pointer to the next node. Next, traversal. You walk from the head, following next until you reach null. Then inserting at the head, just 2 pointer assignments, no matter the length. After that, the double pointer. Node double star lets a function change the caller's head. Finally, delete and free. You unlink a node and release the whole list safely. Let's start with Y. Arrays store elements side by side in memory. That is what makes indexing fast. R of I jumps straight to position I, but it is also what makes insertion slow. To insert into the middle, you must shift every element after it to make a gap. A linked list takes the opposite approach. Each element lives in its own separate heap node, connected to the next by a pointer. Picture a chain of boxes. Each box holds a piece of data and a pointer to the next box. Now inserting or deleting is just a few pointer changes, no shifting, no matter how long the list is. The trade-off is that you lose random access. There is no list of I to reach element I. You have to follow I pointers from the beginning. This is the building block, the node. A node holds two things, a piece of data and a pointer to the next node. Notice something peculiar. One of the fields next is a pointer to the same type, struct node star. This is called a self-referential struct, and it is the foundation of linked data structures. We write the tag struct node before the opening brace, because the next field refers to the struct type from inside its own definition, before the typedef name node is available. Now the definition. A singly linked list is a sequence of nodes, each holding data and a pointer to the next. You reach it through a head pointer to the first node. The last node's next is null, and the nodes are separate heap allocations, not one contiguous block. This figure shows the structure. The first node holds 10, then 20, then 30, and on the far left is head. Head is a node star the program uses to reach the list. It is your only way in. Without head, you cannot reach any node and the whole list would be lost. Each box is a separate heap allocation, made by its own malloc call. The arrows are the next fields, linking one node to the next. And the last node's next field is null, drawn in red, marking the end of the list. Let's write two basic functions. On the left, node create. It mallocs one node, checks for null, sets the data field and sets next to null because a new node starts unconnected. Then it returns the pointer. The sizeof star in idiom gives the size of one node. On the right list print, we start a local pointer cur at head. While cur is not null, we print cur arrow data, then advance with cur equals cur arrow next. When cur becomes null, we have reached the end and the loop stops. The parameter is const node star because printing does not change the list. This walk from head following next until null is the fundamental operation traversal. It is the pattern behind almost every list operation, printing, searching, and counting. The simplest insertion adds a node at the front of the list in just 2 steps. First, create the new node and point its next field at the current head. So n arrow next equals head, and the new node now points to what used to be the first node. Second, update head to point to the new node. Head equals n. Notice what did not happen. No existing node moved, and none of their data was touched. Head insertion is always exactly 2 pointer assignments, whether the list has 3 nodes or 3 million. That constant cost is one of the big advantages of a linked list over an array. Let's watch the 2 steps. We start with head pointing to 10, which points to 20, which ends in null. First, a new node holding 5 appears in green, off to the side. It is created but not yet linked. Step 1, we point the new nodes next to the old first node. So n arrow next equals head, and a green arrow now runs from 5 down to 10. Step 2, we move head to point at the new node. Head equals n the green arrow from head now goes to 5, and the old link from head to 10 is crossed out in red. Follow the chain now. Head 5, 10, 20 null. The new node slid in at the front and not a single existing node moved. Now let's try to put head insertion into a function. This is a natural first attempt and it is broken. List prepend takes a node star head. Inside it creates the new node, points its next at head, and writes head equals new node. It looks right, but it does not work. The reason is that head is passed by value. Inside the function, head is a local copy of the caller's pointer. The line head equals new node changes that local copy, but not the caller's variable. So when the function returns, the caller's head is unchanged. The new node was allocated, but nothing points to it. It is unreachable, a memory leak, and the list was never modified. This is the same pass by value rule you learned for integers. To change the caller's variable, you must pass its address. The fix for an int was to pass an int star. The fix for a node star is to pass a node double star, a pointer to the pointer. In the code, the parameter headPTR is a node double star. Inside the function, star headPTR is the caller's head variable itself. So n arrow next equals star headPTR points the new node at the current first node, and star headPTR equals n writes directly into the caller's head. The caller passes the address of head with an ampersand list prepend of ampersand head. The figure shows the 2 levels. Head PTR points to head. Star head PTR is head. Assigning to star head PTR changes head in the caller's frame. This is the same output parameter mechanism you used with int star, just 1 level of indirection deeper. Any list function that might change the head needs a node double star. Head insertion builds the list in reverse. To keep insertion order, you insert at the tail the end. Appending first requires finding the last node. There are 2 cases. First, the empty list case. If star head PTR is null, the list is empty, so the new node becomes the head and we return. This is exactly why append still needs a node double star, even though it usually does not change the head. Second, the non-empty case. We walk a cursor from the head following next until we find the node whose next is null, the last node. Then cur arrow next equals new node attaches the new node at the end. The trade-off is that every append walks the whole list to find the tail, so it costs n steps, slower than prepend, but it preserves insertion order. Deleting a node means finding it, unlinking it, and freeing it. The key is the unlink. You must make the previous node's next skip over the deleted node. The function uses two pointers cur, the node being examined, and prev, the node before it. The loop advances both until cur holds the target value or reaches the end. If cur is null, the value was not found, so we return. Otherwise, there are two cases. If prev is null, we are deleting the head, so we set star head ptr equals cur arrow next, and the second node becomes the new head. This is another reason we need node double star. Otherwise, prev arrow next equals cur arrow next skips over the deleted node. Finally, free of cur releases the memory. No data is ever shifted, only pointers change. This figure shows the pointer surgery for a middle deletion. On the left before, head points to 10, then 20, marked to delete with a red dashed border, then 30, ending in null. On the right after, we redirect 10's next field, shown in green, straight to 30, bypassing 20. Then the unlinked node 20 is freed. Notice that 10 and 30 did not move at all. Only one pointer changed. In steps, first, find the node and its predecessor, the node just before it. Then redirect prev arrow, next past the target node. Then free the unlinked node. No other node moves. This is the deletion advantage of a linked list. No shifting, just a little pointer surgery. When you are done with a list, you must free every node, but there is a catch. If you free a node before saving its next pointer, you lose access to the rest of the list. Inside the loop, the first line is node star next equals cur arrow next. We capture the link to the next node before free of cur invalidates it. Then we free cur and advance cur to the save next. After the loop, we set star head ptr to null, so the caller's head does not dangle. The principle is the same one from the two-level allocation. Never lose access to memory you still need to reach. Save the forward link first, then free. Let's cover two classic bugs. The first, using node star instead of node double star for a function that changes the head. Here list prepend takes a node star head. It creates the node and writes head equals new node. But head is a copy of the caller's pointer, so changing it inside the function has no effect outside. The caller's head is unchanged. The new node is allocated but never linked in, a leak, and the list looks untouched. The root cause is that C passes pointers by value. The fix is to take a node double star and write through star head ptr, and the caller passes ampersand head. Any function that might change the head needs the double pointer. The second classic bug, freeing a node before saving its next pointer. Here the loop frees cur and then tries to read cur arrow next. But after free of cur, that memory is invalid. Reading cur arrow next is use after free, undefined behavior. It may crash, return garbage, or silently corrupt data, and the rest of the list is leaked because you have lost the link to it. The reason is that free returns the node to the system, so the next field inside it is no longer yours to read. The fix is to save next before freeing. Node star next equals cur arrow next, then free of cur, then cur equals next. Always grab the forward link before you let go of the node. Let's recap. A linked list stores its elements in separate heap nodes connected by pointers. That gives fast insertion and deletion anywhere, but no random access. A node holds data and a next pointer, and the last node's next is null. Traversal walks from head, following cur equals cur arrow next until null. Insertion and deletion just rewire a few pointers, with no shifting of data. The double pointer, node double star, is required whenever a function might change the head, because C passes pointers by value. And when you free the list, always save next before calling free, so you never lose the rest of the list. Next, You have now completed the dynamic memory chapter. In the next chapter, you will put these skills to use with file input and output, reading and writing files, parsing command line arguments, and handling the errors that come up when your program talks to the outside world.